Welcome, curious minds, to the deep dive. Today we're shrinking down way down to peek inside the invisible universe that literally builds everything around us. We're talking about the fundamental building blocks of all matter. We've sifted through a stack of sources, pulling together insights on atomic structure, molecules, the real basics of chemistry. Our mission today, to kind of cut through the jargon, give you a clear, engaging shortcut to understanding these essential concepts. We'll uncover some surprising facts and hopefully connect the dots so you walk away feeling like you've glimpsed the universe's secret code.
Yeah, and it's more than just memorizing facts. Understanding these tiny, unseen components is truly foundational. It's the bedrock, really. All chemical processes, all the principles, they're built on this. Once you grasp this level, it's like seeing the hidden grammar of the material world. So many other complex ideas just sort of click into place.
Okay, let's pull back that curtain then. Matter itself. We touch it, we use it every day, but what is it fundamentally? How does something solid like this desk or, the water in my glass come from the same basic stuff? It starts with realizing all matter is made of these incredibly tiny particles.
Oh, exactly. And for centuries, people imagined these particles as the ultimate indivisible units, what we now call atoms. The word atom itself, it comes from the Greek atomos. Democritus coined it, meaning uncuttable or indivisible. And it's fascinating, similar ideas popped up elsewhere. There was an Indian philosopher, Maharishi Kanmata, who talked about Paramanas, indestructible particles. So for a long time, the atom was seen as like the universe's ultimate Lego brick, indivisible.
Right. And then John Dalton comes along in 1808. He really took that ancient idea and gave it a proper scientific framework, didn't he? Proposing the atom as the basic unit of matter. What was it about Dalton's model that made it so revolutionary for its time? What characteristics did he suggest?
Well, Dalton's work was, profound. It systematized the concept. He argued, first, atoms were the smallest particles. Second, they exhibit all the properties of their element. Crucially, he proposed that atoms of the same element are identical, but fundamentally different from atoms of other elements. That was huge. And this was key back then. He believed atoms couldn't be created or destroyed, just rearranged in chemical reactions. This idea of distinct, indestructible building blocks, that was the real launching pad for modern chemistry.
It sounds pretty straightforward now, maybe, but that must have been a massive shift in thinking back then, to go from this sort of invisible speculation to a concrete basic unit.
Right.
What was the impact? And seriously, how small are we talking? Tiny doesn't quite cut it, right?
Oh, it was a huge leap. It helped turn alchemy into, a quantitative science. And tiny, that's putting it mildly. Think about this. It'd take millions, literally millions of atoms just to cover the period at the end of the sentence. It's a scale that's almost impossible to really visualize properly. But, even Dalton's brilliant foundation got an update. The early 20th century brought an even bigger shift. Atoms aren't indivisible after all.
Ah, right. The subatomic particles.
Exactly. We cracked them open, found the stuff inside. We all know the main ones. Electrons, protons, neutrons. But it's worth a quick recap of their jobs, Electrons, negatively charged, tiny mass, orbiting outside. They're the ones involved in bonding, reactivity.
Okay, so they're like the atom's social particles.
Sort of, yeah. Then you've got protons in the nucleus, positively charged, much heavier. They define the element. The number of protons is the atomic number. That's the atom's ID card. And neutrons, also in the nucleus, no charge, similar mass to protons. They add weight, contribute to the mass number, which is protons plus neutrons, and affect nuclear stability.
So different elements have different numbers of these particles.
Absolutely. But in a neutral atom, the number of positive protons always equals the number of negative electrons. They balance out.
Got it. So we've got these incredibly tiny atoms, each with its own proton-defined identity, but they don't just hang out alone, do they? They like to connect, team up.
Precisely. They rarely stay solo. They combine to form larger, though still microscopic structures, and that's where molecules come in.
Okay. Molecules.
If atoms are the letters, molecules are the words. A molecule is the smallest particle of a pure substance, could be an element, could be a compound that can exist independently and still be that substance. It forms when two or more atoms, same kind or different, chemically combine, stick together.
Like H-heros, two hydrogens.
Yep, that's a molecule of the element hydrogen, or H-hero, two hydrogens, one oxygen. That's a molecule of the compound water.
So it's not just a random jumble. There's a specific arrangement, specific rules.
Absolutely. Molecules have definite characteristics. They're formed by chemical combination. They show all the properties of the substance they make up. And crucially, in a compound, The atoms always combine in a fixed whole number ratio.
Like water always being HO.
Exactly. Never HO or HO. That fixed ratio is fundamental. And the atoms are held together by chemical bonds, these attractive forces. Plus, we can represent any molecule with a chemical formula.
Okay, so there are different types of molecules then,
Yes.
based on what atoms are involved.
Right. Two main types. First, you have molecules of an element made of only one kind of atom. Some elements, like helium, exist as single atoms. We call that monatomic.
Okay.
Others team up. Oxygen we breathe is O-She, two oxygen atoms, so it's diatomic. Ozone in the atmosphere is O-triatomic. And some form bigger groups, like phosphorus, PO, or sulfur, Essa. Those are polyatomic.
Polyatomic meaning many atoms, got it.
And then you have molecules of a compound. These are built from atoms of different elements chemically combined. And this is where things get really interesting. The properties of the compound molecule can be totally different from the elements that made it.
Right, you mentioned water earlier, HO, a liquid.
Made from hydrogen and oxygen, both gases and flammable ones at that. Or think about carbon dioxide, CO. It's a gas we exhale, plants use it. It's made from solid carbon and gaseous oxygen. The resulting molecule has entirely new properties. It's like baking, flour, sugar, eggs. The cake is something completely new.
That's a great way to put it. So you mentioned diatomic, triatomic. Is there a term for just the number of atoms in an elemental molecule?
Yes, that's called its atomicity. It just tells you how many atoms are in one molecule of that element. So helium, He is monatomic, atomicity 1. Hydrogen, H is diatomic, atomicity 2. Ozone, triatomic, atomicity 3. Phosphorus, P, and sulfur are polyatomic with atomicity 4 and 8 respectively.
Okay, atomicity, simple count.
And this ties right back into molecular formulas. They're the symbolic language. CAROs tells you immediately one molecule of chlorine made of 2 chlorine atoms, atomicity is 2, and the notation is really specific. 2H means 2 separate hydrogen atoms.
Okay.
HROs means 1 hydrogen molecule, 2 atoms bonded.
Right.
And 2HROs means 2 separate hydrogen molecules. Getting that distinction is important.
Definitely. Okay, so atoms, molecules. What about when atoms aren't perfectly balanced charge-wise? Like if they gain or lose an electron?
Now you're getting into radicals, or as they're more commonly called, ions.
Ions, okay.
These are atoms or even groups of atoms bonded together that carry an overall electrical charge. They act as a single unit in reactions.
And they have different types.
Yep, 2 main flavors. First, basic radicals, which chemists usually call cations. These are positively charged. They form when an atom loses 1 or more electrons. Think metals like sodium ion, NaO, or magnesium ion, Mg. The ammonium ion, NaQ, is a common nonmetallic example.
So losing negative electrons leaves them positive. Makes sense. What's the other type?
The other type is acid radicals, or anions. These are negatively charged. They form when an atom gains electrons. Most nonmetal ions are anions, like chloride, CaLiO.
Right.
Groups of atoms can also be anions, like the sulfate ion at the arrow.
And how do we name these? Like chlorine becomes chloride.
Yeah, for simple anions from nonmetals, you often replace the ending like -inen or -ine with -iden. So chlorine atom, Cl, becomes chloride ion. Ion, oxygen, becomes oxide. For polyatomic anions, those groups of atoms, the naming is a bit more complex, often using suffixes like -ite or -in, sometimes -iden too.
Okay, so these charged particles, these ions, they're obviously not going to be stable on their own for long. They're looking to balance that charge, right? What is this charge, this tendency to gain or lose electrons? Tell us about how they'll combine.
That leads us directly to the concept of valency.
Valency, heard that term. What is it exactly?
Think of valency as an element or a radical's combining capacity. It's like how many hands it has available to link up with others. More formally, it's often defined based on hydrogen. Since hydrogen's valency is taken as 1, an element's valency is the number of hydrogen atoms it can combine with or displace.
Okay, based on hydrogen is the standard. Can you give some examples?
Sure. Look at hydrogen chloride, HCl. 1 chlorine atom combines with 1 hydrogen, so chlorine's valency is 1.
Makes sense.
Water, HO. 1 oxygen combines with 2 hydrogens, so oxygen's valency is 2.
Right.
Ammonia, and H's. 1 nitrogen combines with 3 hydrogens, valency is 3.
Okay.
Methane, CHO. 1 carbon, 4 hydrogens. Carbon's valency is 4. This handshake count, as you call it earlier, dictates why compounds form in those specific ratios. It's about satisfying each atom's combining needs.
But wait, don't some elements have more than 1 valency? Like they can hold hands differently depending on the situation?
Exactly. That's called variable valency. Some elements aren't fixed. Iron, for example, can form ions like FeO valency 2 or FeO valency 3. Copper can be Co valency 1 or Cali valency 2.
Interesting.
This flexibility allows them to form a wider range of compounds. And it's not just metals. Some nonmetals like nitrogen, phosphorus, and sulfur show variable valency 2. It adds a whole layer of richness to chemistry.
So this valency, this combining power, it's a really fundamental property.
Absolutely. And it's one of the key things that helps make sense of chemistry's grand organizational chart, the periodic table.
Yes, the periodic table. That iconic grid. It's more than just a poster in a science class, isn't it?
Oh, much more. It's a truly genius arrangement of all the known elements currently, 118 of them. They're organized systematically in vertical columns called groups and horizontal rows called periods. It's basically a map of the elemental world designed for systematic study.
Who came up with it originally? I know it evolved.
Well, the major breakthrough came from Dmitry Mendeleev back in 1869. He arranged elements mostly by atomic mass, but crucially, left gaps for undiscovered elements and predicted their properties. That was bold.
Wow.
Later, Henry Moseley discovered the significance of the atomic number, the number of protons, and that became the true organizing principle for the modern periodic table we use today. It's a great example of science building on itself.
So tell us about the structure, rows and columns.
Right. The horizontal rows are called periods. There are 7 of them, numbered 1 to 7. Elements in a period show a gradual change in properties as you go across. The vertical columns are the groups. Historically, they used Roman numerals like IA to VIA and a 0 group. Now, the standard IUPAC system numbers them 1 through 18.
And the groups are where the real patterns emerge, right?
Yeah.
Especially with valency.
Exactly. This is the beauty of it. Elements within the same group often have the same valency, particularly in those main groups, groups 1, 2, and 13 through 18. And because they have the same valency, they tend to have very similar chemical properties.
Can you give an example?
Sure. Look at group 1, or IA, the alkali metals, lithium, sodium, potassium, all shiny, soft, highly reactive metals, and guess what? They all have a valency of 1. Or jump over to group 14, IVA, carbon, silicon. Both typically show a valency of 4. Go further right. Group 15, VA, like nitrogen, often valency 3. Group 16, VIA, like oxygen, valency 2. Group 17, VIA, the halogens like chlorine, valency 1. And then group 18, 0 group, the noble gases, helium, neon, argon. Their combining capacity is 0. They're stable, inert. They don't really do chemistry easily.
That's incredibly elegant. The table structure directly reflects chemical behavior and combining power.
Yeah.
It makes sense why elements in the same column act similarly.
Precisely. It clarifies why, say, sodium and potassium behave alike, even though they're different elements in different periods. It's that shared valency, dictated by their electron structure, which the table reflects.
Okay, so we've gone from the atom itself to molecules to ions or radicals, understood valency, and seen how it all fits into the periodic table's order. Now let's bring it all home. How does all this knowledge, symbols, valency, radicals, allow us to actually write the formulas for compounds, the language of chemistry?
Right. This is where it becomes really practical, the molecular formula. Think of it as the compound's precise recipe. It's a symbolic representation of one single molecule of that compound. It tells you exactly which elements are in it and exactly how many atoms of each, showing their fixed whole number ratio.
And there's a method, a kind of chemical grammar, for figuring these out using the valencies we just talked about. It's not just guesswork.
Not at all. It's logical. The key steps are: 1, write down the symbols of the elements or radicals involved. Usually the more metallic or positive one comes first. 2, write their valencies above or below them. 3, now this is the clever part, you crisscross. You exchange those valency numbers, ignoring any plus or minus signs. 4, write these exchange numbers as subscripts right after the symbol. If the number is 1, you just don't write it. It's understood.
Okay, crisscross the valencies. Why does that work?
It's a quick way to ensure the total positive valency balances the total negative valency, making the compound electrically neutral overall.
Ah, neat trick. What else?
5, sometimes after crisscrossing, the subscripts might both be divisible by the same number. If so, you reduce them to the simplest whole number ratio, like simplifying a fraction. 6, and this is important for radicals. If a radical like OU or SO needs a subscript greater than 1 after the crisscross, you must put parentheses around the radical's formula before writing the subscript outside.
Parentheses for radicals if there's more than 1. Okay, let's try applying that. Can we walk through some examples from the source material?
Definitely. Let's take calcium chloride. Calcium symbol is Ca, its valency is 2. Chlorine symbol is Clu, valency 1. Write them. KaClU, valencies. 2, 1, crisscross.
So the 1 goes to K, we don't write it, and the 2 goes to Cl.
Exactly. You get KKO, Simple as that.
Okay. What about magnesium oxide?
Magnesium is Mg, valency 2. Oxygen is O, also valency 2, right? MgO, valencies 2, 2. Crisscross gives MgO, but wait, step 5, both subscripts are 2. They're divisible by 2.
So we reduce it, divide both by 2.
Yeah. Reduce Mg down to its simplest ratio, which is MgO. That's the correct formula.
Got it. Reduction is key. How about calcium nitride?
Calcium, Cav, valency 2. Nitrogen, N, valency 3, right? Cas, N, valencies. 2, 3, crisscross. The 3 goes to Cav, the 2 goes to N. You get Cas. Can't simplify that, so that's it.
Okay, now one with a radical needing parentheses.
Let's do zinc hydroxide. Zinc is Zn, valency 2. The hydroxide radical is OH, and its overall valency is 1, right? ZnOH, valencies. 2, 1, crisscross. The 1 goes to Zn, don't write it. The 2 goes to OH. Since OH is a radical and its subscript is now 2, which is more than 1, we need parentheses.
So ZnOH.
Perfect. ZnOH. The parentheses show the subscript 2 applies to both the O and the H within the hydroxide unit.
Right. One more, maybe with 2 radicals.
Sure. Ammonium carbonate. Ammonium radical is NHers, valency 1. Carbonate radical is covalency 2, right? NHers, valency has 1 to go crisscross. The 2 goes to NH and the 1 goes to co. Don't write it. Both NHer and co are radicals. NHer needs a subscript of 2.
So parentheses around the NH.
As Her, exactly. And the co just needs a subscript of 1, so no parentheses needed there. The final formula is NHer.
That step-by-step process makes it really clear. So these molecular formulas, they pack a lot of information, don't they? What's the real significance?
Oh, huge significance. A formula like, say, H arrow for sulfuric acid tells you so much at a glance. First, it represents one molecule of the compound. Second, it tells you exactly which elements are present: hydrogen, sulfur, oxygen. Third, it tells you the precise number of each atom in that one molecule. 2 hydrogen atoms, 1 sulfur atom, 4 oxygen atoms.
And the ratio too, right? 2 to 1 to 4?
Precisely, the fixed whole number ratio. And fourth, because you know what atoms are there and how many, you can actually calculate the molecule's molecular mass by adding up the atomic masses of all the individual atoms. It's incredibly powerful. It's the basis for stoichiometry, for understanding reactions quantitatively.
And if we saw something like 2 H-arrows?
That just means you have 2 separate molecules of sulfuric acid. The formula H-arrow itself doesn't change, just the quantity you're considering.
Wow. What an incredible journey we've taken. From the almost philosophical idea of the indivisible atom through discovering its inner parts, seeing how atoms team up into molecules, understanding their charges as radicals or ions, grasping valency as their combining power, seeing the beautiful order of the periodic table, and finally, learning the practical language of chemistry, how to write those molecular formulas. It feels like we've decoded a fundamental layer of reality.
That's a great way to put it. It really is the instruction manual. Atoms are the letters, molecules are the words, valency and bonding are the grammar rules. Understanding this foundation, it just opens up the entire field of chemistry. It explains why things are the way they are at a material level.
And that's really the goal of this deep dive, isn't it? To take these concepts that can seem abstract or intimidating and make them understandable, tangible. Hopefully you listening now feel like you've got a really solid footing in the basics of chemistry.
Absolutely. And maybe a final thought to leave you with. If you just stop and consider that everything around you, the air, the water, your phone, your body, is all built from these invisible particles, all interacting according to these precise, elegant rules of combination and valency we've talked about, it makes you wonder, doesn't it? What other mysteries could we unlock if we understood these interactions even more deeply? What could we build? What processes could we master? This foundational knowledge, it's really just the starting point for understanding and maybe even shaping the material world. Makes you think,